gas stoichiometry. When we are dealing with masses, or you're dealing with anything that is a pure substance, be it a solid, a liquid, or a gas, that is when you have to get moles from mass over molar mass. That's kind of one of three ways you can get moles in Chem 20 by the time you've learned everything. For a gas, if you haven't weighed it, you won't be able to use this strategy. We're going to have to use the ideal gas law. So I've rearranged PV equals nRT to moles, and that's how we're going to get moles in our gas stoic. Now you might have to rearrange PV equals nRT differently to answer for volume if that's what the question asked about. Within gas stoic, you're only going to be solving for moles or solving for volume, okay? Unlike questions that you might get within the other parts of the gas unit. We haven't gone to solutions yet. When you have solutes and solvents, you'll learn another strategy for getting moles, the third one. So my first question, what volume of water vapor is produced when a kilogram of natural gas is burned at standard ambient temperature and pressure? So this is water vapor. So this isn't a liquid volume we're after, it's a gas volume we're after. So that tells us we're going to have to use some gas law relationships. Okay. So natural gas is mostly methane. In Chem 20, we would tell you it's CH4. In Chemistry 30, it's one of those things you'll learn to decode it. So you should be able to, on your own, do a combustion reaction given the fuel. So methane plus oxygen is going to make CO2 and water. Now that is not balanced yet, so as you're writing it down, you could put in the proper subscripts. Okay. I solve all of these using ICE tables as an organizational tool. We have one carbon on both sides. We have 4 H's in the beginning, and they come in pairs in water. So I need 2 pairs or 2 waters to get 4 H's. I have 2 O's from my carbon dioxide and 2 more O's from the 2 waters. So that gives me 4 O's. So I need 2 pairs of 4 O's, 4 oxygens at the beginning. Now we're balanced. I'm going to set up the plan to solve this exactly like you would in gravimetric stoic with masses, or in solution stoic if it was a solute in a solvent. So where can we start? We have 1 kilogram of natural gas, that's our methane. So I'm going to start with my methane, get that column, assume it all runs out. Step 2 is always your change, and step 3 gets you to your answer. We want volume of water vapor, so we're going to need to get moles of water vapor first, and then we can turn that into a volume. Okay. We're going to assume that all of the methane burns. So how much methane do we have? Well, that's a kilogram. That's gravimetric stoic. So we're not doing any gas relationships yet because that's a mass. So CH4, I'm going to get moles from mass over molar mass. So I need grams, not kilograms. So kilo means 1,000. We have 1 kilograms. So you multiply that by 1,000 to get to the base unit. The molar mass for 1 carbon and 4 H's is 16.05 grams per mole. So I get 62.3 I'm going to keep one extra digit to show on the board. You'd keep all the digits in your calculator. So we have 62.3 moles. Our original data had 2 sig figs, so I'll be rounding to 2 sig figs at the very end. Okay, so we're going to assume all of that 62.3 moles reacts away. There's nothing new yet. The stoic step is the same. We do the change. We take the given change and we want to turn it into the water or the required. So we multiply by the required coefficient. We're requiring water vapor, which has a 2 coefficient. The given chemical, the methane, has a 1 coefficient. Okay. We get double the water moles compared to the methane moles put in. So we're going to make 125 moles. Okay. Now again, I've kept all the digits. I have 124.6 something something. Okay. I've just rounded for the sake of the board, writing it on the board. We would have no water vapor at the beginning, so we're going to make 125 moles of water vapor. Now that's not the question. We want water of this gas. We want volume of this gas, not moles. So PV equals nRT would be your starting point, the ideal gas law. We want volume you end up dividing both sides by pressure, and you can isolate for volume. So we need N, we need R from our data sheet, we need the temperature. We can get that from SATP, and we need the pressure, and we can get that from standard ambient temperature and pressure. So we have all those pieces either in our question or from a data sheet or formula sheet. So moles, again, I'm writing 125, but keep all the digits from your calculator. So that's N, R, 8.314 kilopascals, liters, moles, Kelvin, times our temperature. So standard ambient temperature and pressure. The standard ambient one is the warmer one. It's the 25 degrees Celsius standard. The STP is the colder 0 degrees Celsius. But we need it in Kelvin, so it's 298 Kelvin. Okay. Now you could keep 298.15. We're going to be rounding to 2 sig figs at the end, and I've already got 3 in my temperature. Last, the pressure. The pressure at STP is 100 kilopascals. Okay. All our units match. The gas constant is setting our units. We had kilopascals in it, so we had to use kilopascals. Moles and moles, Kelvin and Kelvin. So the only thing left is liters. So I'm going to write down kind of what was in my calculator. I got 3,088.9. Too many digits, I'm not done. And I'd have to round this down to 2 sig figs. So I'm going to keep the 3, and then I'm going to round that second digit as my second significant figure. So 3, and then the 0. The digit after it is an 8, so I'm going to want to round it up. So I get 3,100 liters. We got a big number, so you might be thinking, oh, did I make a mistake? But we put in a kilogram. We put in a lot of reactant. So getting a fairly large volume makes sense. Okay. Now, within the chemistry program in Alberta, we tend to use prefixes. In physics, in Alberta, you tend to maybe use scientific notation with a number like this. Okay? Particularly in Chem 30, you got to get used to switching to milli or kilo, okay, to get rid of some of those ambiguous zeros. Okay? So you might be asked on a test to report this in kiloliters, counting by thousands. Okay? So I just need to divide this by 1,000, which is moving the decimal 1, 2, 3 times. Okay? So it's kind of nicer scientifically to express this answer as 3.1 kiloliters, and then those placeholder zeros aren't there, and there's no ambiguity. So that's my first example, a little bit of gravimetric stoic, a little bit of gas stoic. You rarely get a question that is 100% gas stoic. So let's do a second one, and then you're going to do the third one. So what mass of sodium, so sodium is a metal, so that'll be gravimetric type stoic, is required to make 3¼ thousand liters of hydrogen gas at standard ambient temperature and pressure. You do not have enough information there to figure out what the reaction is. So I would have to give you more details. Okay? You knew there was sodium put in and you knew there was hydrogen put out, but it's sodium reacting with water. Going to do a single replacement. Sodium is going to grab an O and an H and spit an H out elementally. And H's come in pairs elementally. Again, this usual organizational tool, initial, change, and end amounts. Where am I going to start? So mass of sodium is the question, so that's where we're going to end up. So that's going to be here is our finish line. We're going to have to start using this volume of hydrogen gas. So that's going to be our 1. We're going to finish there. And our required over given is always our middle step. So that's a volume of hydrogen gas. So this is where our gas laws are going to come in. We're going to need moles for our ice table. So we need to take the pressure of the gas times the volume of the gas divided by R divided by T. And all this will be for hydrogen, H2. So pressure, we're under standard conditions again. So that's 100 kilopascals. Those 2 zeros are significant. Okay, when we write 100, it's a little ambiguous, but they are measured. They're part of the standard. Times volume, we need liters, because when I get to my R on the bottom, that's 8.314 kilopascals liters over moles Kelvin. So I need my gas in liters. We have 2¼ thousand liters. To get rid of the kilo, we multiply by 1,000, so that's 3,250. We have a non-significant 0 shows up as a placeholder. Last, we need our temperature from STP, and that's 298 Kelvin to 3 sig figs. Okay. Again, you could use the 0.15, 298.15. Kilopascals cancel, liters cancel, Kelvins cancel, and we get moles on the bottom of the bottom. moles to the -1 to the -1, which is really just moles to the 1. And I got 131 moles, rounding it for the sake of putting on the board. So we're not done. You'd have all the digits in your calculator, but there was 131 moles made. We would assume there'd be no hydrogen at the beginning, so the reaction must have made all 131 moles, and then we can work backwards to predict how much sodium would be required to do that. The required is the sodium, which is a 2. The given is the hydrogen, our given data in red. That has a coefficient of 1, so we need double the moles of sodium to make our hydrogen. So that's 262.2 something moles. Again, I didn't write out all the digits. 3 sig figs was given, so I'm showing at least 3 sig figs in my solution. We're going to assume all the sodium put in reacted away. So 262 moles must have been put in and completely used up. We need to answer the question, which is mass. So that's gravimetric stoic to end this question. Mass is molar mass times moles. Molar mass sodium comes in ones. There's a 1, invisible 1 subscript after it. The fact there's a 2 in front does not change the molar mass of sodium. It's just 1 sodium. So the atomic mass of sodium is 22.99 grams per mole in our data booklet, times our 262.2 moles. Moles and moles cancel. We're going to get our mass. Now we made over 3,000 liters, so we're going to get a fairly significant mass. I've got too many digits. I'm going to have to round that, but I got 6,028 grams are required. I'm going to round this to 3 sig figs. So I'm going to keep the 6, keep the 0, and then I'm going to round that as my third significant figure. So 6,000, and the 2 I'm going to round up because there's a digit greater than 5 after it. So I'm going to round the 2 up to a 3, and then I need a placeholder 0, a non-significant digit to keep everything in the right place. So 6,030 grams. Again, this is where kilograms could be nice. If I ask this on a quiz and I don't tell you the units, you could use either. Okay? But it'll be common in the chemistry program to make you report this in kilograms. So divide by 1,000, 6.03 kilograms, and there's no non-significant digits in the kilogram answer. So our last question that you're going to solve, what mass of calcium metal reacted with extra water and it made a little over 10 liters of hydrogen gas, a little over an atmosphere, and 33 degrees Celsius? So I'll let you work on this and I'll slowly put up the answer to pieces after I think you've had enough time to get through those calculations. So the answer to this question, I have to start with moles of hydrogen. Pressure times volume over R times T. The pressure took the most work to solve here. The atmospheres had to get converted to kilopascals. So when I did that conversion, I got 106.4 kilopascals. Volume was 10.3 liters. .314 kilopascal liters moles Kelvin times temperature would be 33 on top of the 273, so 306.15. So I got 0.4307 moles. So with the correct kilopascals, you got the moles, and it's fairly straightforward to finish. We want mass of calcium. We're requiring calcium. It's a coefficient of 1, hydrogen's 1, so it's the same moles. We'd assume there's no calcium at the end. And last, our calcium mass, molar mass times moles. Metals come in ones, 40.08 grams per mole. And to 3 sig figs, I got 17.3. So hopefully everybody, when you were solving this, you did this gas calculation, you got that moles, and you just left it in your calculator. You wrote something down on your paper, and you just kept pulling that number forward. You probably did the 1/1 in your head, and then you multiplied by the molar mass, and you were done. So that wraps up stoic and wraps up gas stoic.